Hey everyone, in this video we are going to go through Newton's laws of motion. This is probably a big topic, very important in this unit to understand these laws of motion, and there are three laws of motion. Now Newton's laws are named after Sir Isaac Newton, and Sir Isaac Newton was a physicist or a scientist who you might know because of the story of him discovering gravity when an apple hit him, which isn't necessarily a true story, but it's a legend that kind of gets told a lot. And Sir Isaac Newton, one of the first physicists to really formalize the field of mechanics and dynamics that we are learning about, and he developed three laws of motion. And these three laws of motion are foundational to this, and they're going to be used a lot for solving problems. Now, the couple things to know about these, there are three laws, like I say. The first law is just a concept, and there is no formula related to it, but the second and third laws have both a concept and also a mathematical formula associated with them. And so that's how these laws work. And we're going to go through each of them in this video. I'm going to hopefully provide you timestamps in the description so you could just switch to the ones that you don't understand or that you would like to learn a little bit more about. And that's how this is going to go. Okay, so let's start with the first law. Newton's first law of motion, which some people also call the law of inertia, but I'm going to point out in a second why that's not exactly accurate. I'm going to start by reading it in the kind of technical way that it's usually cited in textbooks, which might not really be helpful to you, and then I'm going to kind of explain it in a way that hopefully will be helpful to you. So the way it's cited in textbooks is like this. Newton's first law says that if the net external force on an object is zero, the object will remain at rest or continue to move at a constant velocity. Okay, so let's kind of dissect what that means. So it starts with if the net external force. Now, net external force we talked about last time when we were calculating net external forces, which is literally just the overall force of a system. Remember, for instance, we would have diagrams that look like this, these free body diagrams, and we would calculate this value, which was F net, sometimes in the X or the Y. And that is the net external forces for that system. And what Newton's first law is saying is Newton's first law applies only if the net external force is zero. That means if the forces which are coming in exactly balance them out. So, for example, if these two forces here are like 10 newtons and another 10 newtons, this will balance itself out because this force exactly negates that force. If this is force 1 and this is force 2, the calculation of F net here is going to literally be F net equals F1 minus F2. And if those values are both 10 newtons, then you're going to get 0. And so in these sorts of circumstances, when all the forces balance each other out, you have a situation where Newton's first law applies. And it says that if the net external force on an object is 0, then the object will either remain at rest, which means it just isn't going to move, or it will continue to move at a constant velocity. And this is kind of intuitive. Basically what it's saying is that if there are no forces being applied on an object, or that the forces are balanced, but either way the net force is 0, then an object is really just going to keep doing what it was already doing. If it was already just moving at a normal velocity, it's just going to keep doing that. And if it wasn't moving, it won't start moving. This kind of is just a normal fact of life. If you put a thing down on a table, your anticipation of that is that it will not just suddenly and spontaneously move. It will need a force acted on it, say you pushing it along the table or something else. And that's because if you put an object on a table like this, there's a normal force and a gravitational force, which we talked about before. And these forces will exactly balance themselves out so that F net, in this case in the y direction, is going to exactly equal the positive normal force minus the gravitational force, and these will equal 0. And that means that the box will not move, it'll just sit on the table. Now this law is also often called the law of inertia, and the law of inertia is slightly different, but they really both mean the same concept. Newton's first law explains basically the requirements that you need a net external force in order for an object to accelerate. Otherwise, it'll just keep doing what it's doing. The law of inertia explains why this is true, which is basically because of kind of a fundamental property of the way our world works. Now, in a future video, we're going to learn a bit about this distinction between mass and weight, and you'll probably start to understand the connection between mass and inertia, because those are very related concepts. But for now, the main thing to understand about this law is a couple facts. One thing is that objects at rest want to stay at rest. That means that you need to provide a force or an imbalance in forces for an object that is at rest to suddenly decide not to be at rest. Otherwise, it will just be at rest by default. Similarly, though, objects that are in motion tend to want to stay in motion, and they're going to try and do that again unless you imbalance the forces and give them a force. Another rule is that changes in velocity need to be triggered by a net external force. So that means that, a box, an object, will not suddenly change its velocity. It will not suddenly accelerate without you providing it a net external force. And finally, internal forces do not change an object's motion. And these are the forces inside a system. A really real-life example of this is if you're in a car and you, kick the front seat from the back. You didn't alter the motion of the car. The car is still moving. There's not much you can do from inside a car to change the way the car moves, unless, of course, you're driving it. So there's no internal forces which will change the external forces, make the object's motion any different. So that's pretty much it for Newton's first law. Remember that it's basically saying that as long as there is no imbalance of forces on an object, that object will just keep doing what it's doing. If it's at rest, it'll stay at rest. If it's in motion, it will stay in motion. Okay, now for Newton's second law. Before we start Newton's second law, I'm going to take a second just to explain this mathematical operator. In mathematics, you often see a lot of things which are like, okay, x equals y. And we call these equations, and it's basically saying that the thing on the left is equal to the thing on the right. But not always will you see that equal sign. There's another mathematical operator which looks like this. This kind of honestly looks like a fish. Is called the proportionality operator, and it expresses the concept of proportion. Now, if you don't know what proportion is, you might want to look it up if this simple explanation doesn't really help you, but basically when a thing is a proportional to another thing, so if x is proportional to y, like you're seeing here, what it basically means is if x gets bigger, y will also get bigger, and if x gets smaller, y will also get smaller. And it'll do that at the same kind of rate. So the numbers might be different, but it'll move at the same rate and in the same direction. This concept, x being proportional to y, meaning, as y goes up, x goes up, and vice versa, is called direct proportionality. The opposite of direct proportionality is called inverse proportionality, which we literally do by taking the reciprocal of the y. And inverse proportionality means that as x goes up, y goes down, and as y goes up, x goes down. So now they are opposite instead of the same. Don't worry too much about this. This is just a little bit of background because you might see direct and inverse proportionality in textbooks or in other explanations of Newton's second law. Now, the scientific definition of Newton's second law is this. If the net external force on an object is not zero, the object will accelerate in the direction of this force. The magnitude of the acceleration is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. Now that's a whole lot of stuff, so let's kind of break that down. First thing it says is if the net external force on an object is not zero. We just talked about Newton's first law, and we talked about how it says if the net external force is zero. So Newton's first law deals with scenarios in which we have no net external force, the force is zero, and Newton's second law deals with the opposite scenario, which is when we do have some sort of net external force. In that case, Newton's second law says that the object will accelerate in the direction of the force. Now this is pretty self-explanatory. If you have a ball, and you kick the ball in this direction, this is a foot, believe it or not, if you kick it in this direction, you're applying force, you would not then expect the ball to go backward toward you. The ball is going to accelerate in the direction of the force. That's kind of just self-explanatory. That's the first kind of part of Newton's second law. The object will accelerate in the direction of the force if the net forces aren't zero. Then it talks about the magnitude of the acceleration, really just how much acceleration you have. And it says that the magnitude of the acceleration is directly proportional, we just talked about proportionality, to the magnitude of the net force. So the magnitude of the acceleration, so here's acceleration, is directly proportional to the magnitude of the net force. Here's our net force. So what is this saying? Really, it's complicated words for something pretty simple and intuitive. Basically, the harder you kick the ball, the faster it will accelerate, which is kind of intuitive. The more force you apply to something, the more you expect it to change its speed. You want it to accelerate faster. And so we say that the acceleration is proportional to the net force, or vice versa. I mean, you could say this the opposite, doesn't really matter. Proportionality goes both ways. So as you increase the force you apply, the object will also accelerate more, or it will change its velocity faster. The last part of this law is saying that the magnitude of the acceleration is inversely proportional to the mass of the object. So if we have the mass of the object, that is inversely proportional to the magnitude of the acceleration, or to put it an opposite way, again, because these things go both ways, this. So acceleration is inversely proportional to the mass of the object. Now, we talked about mass in previous videos. I said it's kind of like weight, but physics has a kind of more specific definition of it. We're going to talk about this specific definition later. For now, to say it's kind of like weight is clear enough. Basically, mass is, kind of how heavy an object is-ish. So, this also makes a lot of sense. It's a lot easier to push a 3 kilogram box than it is to push a 40 kilogram box. That's kind of intuitive. And that means that we need less force to push the 3 kilogram box and more force to push the 40 kilogram box. Which also means that if we were to apply the same amount of force to the 3 kilogram box and to the 40 kilogram box, the 3 kilogram box would move a lot more than the 40 kilogram box. That means that the acceleration would be a lot greater for the smaller box. The less mass the box has, the greater the acceleration if the force is the same. That means that as acceleration goes up, mass goes down, or as mass goes down, acceleration goes up. The smaller the object, the less force you need to make it go a certain acceleration. That is basically the core of this law, and they're stated with these sort of proportionalities, but there's one equation that's really encompassing the entire concept of this law, and you've probably seen it before. And it looks like this. You might have also seen it without all the extra symbols, just as F equals ma, which is force equals mass times acceleration, and this is the core of Newton's law. The net external forces are equal to the mass of an object times the acceleration of an object. And this is a really powerful formula that allows you to do a lot of questions that involve single bodies moving in different ways with forces and mass and acceleration. Because by having such a formula, we've now linked three things kind of together. We now have a concept of forces, we have a concept of the mass or kind of weight of the object, and we have a concept of acceleration, which was from kinematics. And this kind of connects everything in this one really critical formula. Now, for now, I'm not going to get into the details of using that formula. We're going to do that probably in a separate video about solving practical word problems using Newton's laws, because that's a whole subject in of itself. But for now, it's more important just to understand the implications of the formula. It means a couple different things. We learned already that objects with a force, a net external force acting on them, are going to accelerate in the same direction. Remember, if you kick a ball, that ball is going to go in the same direction as where you applied the force. The acceleration of the object will result from the change in speed or direction because you're applying a force. It's going to change speed, it's going to change direction, it's going to gain an acceleration. This is pretty intuitive. And an object's mass affects the acceleration. The higher mass gives it a lower acceleration, inversely proportional. That is at its core what Newton's second law is all about. And that's really all you need to know for now. Just make sure that that concept is really ingrained. Okay. Finally, let's take a look at Newton's third law. The way it's stated in textbooks is for every action force, there is a simultaneous reaction force which is equal in magnitude but opposite in direction. You might hear this simplified to every action has an equal opposite reaction. And what does this really mean? Well, it has a couple things that it means, and this is probably the most confusing or maybe counterintuitive law when you first think about it, but I promise it does eventually make sense. Basically, it comes with this formula that says that if you have a force of an object A on a different object B, then that's going to equal negative of the force of the object B on object A. Basically, for any action force where you're like doing an action, I don't know, pushing on someone, there's a simultaneous reaction force, so the force that you get back, which is the same amount of force, but it's going in the opposite direction. So a really good example of this is skating. You've probably seen maybe in the Olympics figure skaters, or just you've seen two people skating around together. And if you have these two people, and they're kind of skating on ice. Now the reason that skating on ice is good is because ice has very little friction, and we can pretend that it has no friction just for this demonstration. So these two people are, sitting here, chilling, skating on ice. But if this one person, let's call him person A and this person B, if this one person pushes on person B, well, what's going to happen? He's pushing on person B, but what will happen is because he's doing an action force, there is going to be a simultaneous reaction force that is equal but opposite in magnitude, which means he's going to get a force back which is equal. Now, this might not be super obvious when you have a person, but it will definitely become obvious if you take person B away and you replace him with a wall. Now, walls don't move. That's hopefully why there's walls. If you have a wall that moves, probably an issue. So, if person A applies a force like this is force A on B, because the body A, this person, is applying a force on B. So that is this thing here. Well, if he's on ice, you'll notice, you can try this if you go skating, if you go and slam into the boards at the side of a hockey rink, what's going to happen is you are going to get pushed away from the boards, and it'll probably hurt. But you're going to get pushed away, and that is this force, the force of B on A. And the important thing to understand about this force is that these two forces are equal. They have the same magnitude, they are the same amount of newtons, just going in opposite directions. This is pretty intuitive anytime you hit something. If you hit a wall, you are going to kind of bounce off of the wall basically in the opposite direction, but the same amount of force will be applied. And this is a very important foundation of our world, and it kind of has a couple different things that result. One of them is the concept of pairs. Basically, all forces come in pairs. It's not possible to have a force that doesn't exist without an opposite force. Every force comes in a pair. Now, when I bring this up, you might be thinking, oh, yeah, I know an example of a pair. The normal force of an object that's on a ground compared to the gravitational force. That's a pair. And you are right, these forces are equal but opposite, like it says in this law. But this example is not an application of Newton's third law, and that's for one very important reason. This pair of forces is not an action-reaction force because they are on the same thing. You don't have action-reaction forces just taking place within one body. Newton's third law only applies when you start to have multiple bodies happening. Equal and opposite, like normal and gravitational forces usually are, does not necessarily mean action-reaction. You need two different bodies for instance, a body here and a body here, where one is pushing on one, and you're getting a reaction force from the other. This here is an application of Newton's third law. This is not. Newton's third law always requires two separate bodies, or more, never just one. If you're ever dealing with something which is solely one body, then you're dealing with Newton's first and second laws, but not Newton's third. Newton's third law only comes into play when you have multiple objects that you need to do stuff with. That's basically the gist of it. Newton's third law is telling you that the force of A on B is going to equal the negative force of B on A. Like most of these other laws, all of them start to make more sense when we do practical problems with numbers in them, which will be coming, I promise. And that'll start to make a whole lot more sense than they probably do now. For now, it's most important to just understand the concepts so that you could explain the theory of these forces in, say, a short answer question on a test, if you had to kind of explain what was going on with these forces. That's all for this video. Thanks for watching. Hopefully this was helpful, and I'll see you guys again next time.